So aldol condensation. See, aldol condensation is the reaction given by aldehydes and ketones that contain alpha hydrogen atom. It is given by aldehydes and ketones that contain alpha hydrogen atom. If we take ethanol, this is the functional group. This is alpha carbon and this is alpha hydrogen. Just now we have discussed the acidic character of alpha hydrogen atom is triggering aldol reaction. So aldol reaction is given by those aldehydes and in fact ketones. This is the functional group and this is alpha carbon, alpha hydrogen. Of course, this is alpha carbon, alpha hydrogen. So those aldehydes and ketones which contain alpha hydrogen atom in it give aldol condensation, right? Two molecules will condense to form a special product. If you take say for example ethanol, the two molecules condense in dilute alkali solution, which is a very slow and reversible process, right? And what the reaction product obtained is you get CH3, CHOH, CH2, CHO. In fact, you can see the two ethanol condensed giving this product. You can easily understand. You can easily figure out how that two ethanol condensing CH3CHO. You see that CH3CHO, molecule number 1, and molecule number 2, CH3CHO. Hope you understand. It is a condensed product. And what is the speciality of that condensed product which you analyze? You can understand it is beta hydroxyaldehyde. It is beta hydroxyaldehyde. This is the functional group. This is alpha carbon. This is beta carbon. You get a hydroxyl group coming at a beta position, and this is beta hydroxyaldehyde. Since there is a aldehyde group and there is a alcohol group, we call it as aldol. Aldol. The name aldol arrived in that sense. Aldehyde with the alcohol. Aldol. And this aldol has got one more speciality. This, upon simple heating, water will be eliminated. Beta hydroxyaldehydes easily undergo dehydration process, and this OH group along with one hydrogen from here eliminated as water, and you get a double bond in this region. You get unsaturated aldehyde. Some of you may be aware of the very famous crotonaldehyde. This is called a crotonaldehyde. In fact, it is 1, 2, 3, 4 but-2-enol. But-2-enol. That is the molecule, right? So aldehydes or ketones which got alpha hydrogen in it undergo a condensation process. You get aldol. What is aldol? Beta hydroxyaldehyde or beta hydroxy ketones will be called ketols. Whether aldol or ketol, we commonly refer it as aldol condensation. It is driven by alpha hydrogen atom. The acidic nature of alpha hydrogen actually trigger the reaction. Hope you get the point. Okay. So this is what aldol product given by ethanol. Let us examine how it is given by say one ketone. One ketone, say acetone, will give you aldol product in what way? CH3, CO, CH3, two molecules in presence of dilute alkali will condense like this. CH3, COH, CH3, CH2, COCH3. Once again, you can see it is beta hydroxy product. This is the functional group alpha carbon, beta hydroxy ketone. It may be called as ketol. The reaction normally called as aldol condensation, which upon heating will eliminate water very simply. And this OH group along with this hydrogen, you get a double bond over there. You see, you get CH3, CH3, double bond CH, CO, CH3. You must have the you must have the thinking ability, thinking why the dehydration happens over this region, not this region. It can so be happen, no? OH group from here and hydrogen from here is eliminated, and thereby you get a double bond here. Why not that happens? Similarly here, OH group from here and hydrogen here is eliminated and you get a double bond over this region. Why not it on the other side? OH from this side and hydrogen from this side eliminated, so that you get a double bond on that region. Why not that is happening? You must have that kind of thinking, and I'm leaving to you. You please comprehend why. You please try to reason out why it is not happening in that way, rather it is happening this side. And that in fact gives you answer why so, and why this dehydration is very simple in case of aldols, even without the help of a dehydrating agent. Upon heating you get dehydration process. So this is the product obtained. 1, 2, 3, 4, 5. So it is 4-methyl. Please verify. 1, 2, 3, 4. 4-methyl. 5, pent. 4-methyl pent. 1, 2, 3. 3 in 1. 2 on. 4-methyl pent. 3 in 2 on. Very famous, known as methyl oxide. This is what aldol condensation. Aldol condensation is triggered by aldehydes or ketones with an alpha hydrogen atom. Right? Let us try to find out what is the role of alpha hydrogen atom, or how this reaction can be scripted. How we can understand the script, or how we can write a script on this reaction. I mean the reaction mechanism. How this reaction is happening. Very, very important. Not referred in the textbook, but still we must take our effort to learn how this reaction is happening, or what is the story behind. Let's go through. The reaction happens in such a way. You see that? Let me write the reaction once again. 2CH3CHO with a dilute alkali, you get CH3CHOH CH2CHO. Upon heating, water is eliminated. You get CH3CH double bond CHO. This is what the reaction. Let's see the story behind. How this reaction is happening. The mechanism involved in the reaction. See, let's start with the molecule number 1, which got alpha hydrogen like this. And already commented, this is alpha carbon, this is alpha hydrogen. Alpha hydrogen is acidic in nature. Quite naturally, it will be attacked by a base. So alpha hydrogen, acidic in nature, attacked by a base. So this bond pair electron between carbon hydrogen will be shifted to carbon, and thereby you get a carbanion. CH2CHO. You get a carbanion. We have discussed a few minutes back how this carbanion stabilized by resonance, and hence the hydrogen act as acidic in nature. And now the second molecule is introduced. The second ethanol molecule, which is polarizing as O- and C+, and that C+ is attacked by this nucleophile. The carbanion CH2-, a very good nucleophile, will be attacking on the carbonyl center, electrophilic center of the next molecule. So what is the result? The result is you get CH3, CHO-, CH double bond turn single bond, O-, connected to CH2, CH2, CHO. I repeat, CH3, CHO minus connected to CH2, CHO. And now this O minus will abstract a proton from the solution and you will get aldol. This in fact is aldol. This in fact is aldol, sorry. This in fact is aldol. Functional group alpha carbon, beta hydroxy aldehyde, which upon simple heating there will be elimination of water, OH and H is out and you get the so-called crotonaldehyde like this. This is what the story involved in the reaction. This is what the mechanism involved in the reaction, or this is the way you can understand the script or write a script for the reaction concerned aldol condensation. Let me repeat. This is the molecule number 1 having alpha hydrogen atom attacked by the base and you get a carbanion. And that carbanion attack the electrophilic center of the second molecule and undergo condensation. You get it like this, proton capture, you get aldol. This is what the aldol is. And that aldol, simple heating, you get dehydration, final condensed product. Clear? Or even you can simply understand, it is so understood, CH3CHO plus CH3CHO. Imagine this hydrogen atom and this oxygen atom and 2 hydrogen out as water connect with a double bond. You get this, isn't it? 1 oxygen gone, 2 hydrogen gone and connect it with a double bond, CH3CH, CH3CH, double bond CH, CHO. That's another very simple way to understand the aldol condensation reaction. Remember, it is given by aldehydes with the or ketones with the alpha hydrogen. If you take formaldehyde, there is no alpha hydrogen. If you take formaldehyde, there is no alpha carbon E1. If you take benzaldehyde, there is alpha carbon but no alpha hydrogen. So molecules without alpha hydrogen cannot trigger aldol condensation. Please be very careful. Aldehydes without alpha hydrogen cannot trigger aldol reaction. I never said it cannot be the part of aldol reaction. They can be the part of aldol reaction by getting attacked, not going for an attack. Cannot trigger the reaction, cannot start the reaction. It can be a part of the reaction. That's a different story. I hope it's clear, right? This is called the aldol condensation. This is called the aldol condensation, and whatever we have seen with the ethanol, whatever we have seen with the ethanol, with acetone, this is called a simple aldol condensation or self-aldol condensation. Simple aldol condensation or self-aldol condensation. Which means there can be mixed aldol condensation. That is the point. There can be mixed aldol condensation. Suppose we are taking a mixture of, say, ethanol and propanol. Suppose I am taking a mixture of ethanol and propanol. This is aldehyde 1 and this is aldehyde 2. In fact, you can get how many products? How many possible products you can get? You can get 4 products. What are the 4 products? Product number 1, it is A1 condensing with A1, self-condensation, already written. Product number 2, it can be A2 condensing with A2, self-condensation. So A1, which contain alpha hydrogen atom, can participate in aldol condensation. It may give self-condensation product. This also contain alpha hydrogen, can trigger aldol reaction, can participate in self-condensation. And the other 2 possibilities, hope you remember and understand. It is third one, A1 can attack A2 And obviously the fourth one, A2 can attack A1. So reaction started with A1 attacking on A2, that is called a cross aldol product or mixed aldol reaction. Or A2 reaction triggered by A2 attacking on A1, that can be another one, right? So let us try to understand. This is A1, this is A2, this is A1 and this is A2. Let us see what are the products obtained. Already A1 product already written. A1 product already written, isn't it? Already written. What about A2 product? How can you get A2 product? This is A2. This is A2, which is attacked by next A2. It is this way you can understand. You see, this is the functional group CHO group. I am going to condense over this CHO oxygen is condensing with the alpha carbon hydrogen. That is the way it is happening. So it is this oxygen and H2 from here out as H2O. You will get the product. You will get the product. So CH3, CH2, CHO, this oxygen and 2 hydrogen from this alpha carbon out as water. You get the final product. And in fact, the aldol product will be like this. Aldol product will be like this. CH3, CH2, CHOH, CH, CH3, CHO. That will be the aldol product. Functional group alpha carbon, beta hydroxy aldehyde. Isn't it? Now dehydration product will be OH gone and H gone. You get a double bond here. Same thing I am explaining here. OH, oxygen and H2 out. The final product will be CH3, CH2, CH double bond, C, CH3, CHO. You see that? CH3, CH2, CH3, CH2, CH connect with a double bond and H2 gone, C, CH3, CHO. That is the final condensed product. And you know this is A2 product. So A1 product already written. Now it is A2 product. Self-condensation. Now what about A1A2? How it is going to be A1A2 product? A1A2 product. You see A1A2 product. This is A2 being attacked by A1. This is A2 being attacked by A1. A carbanion is formed over here. A carbanion is formed over here and that carbanion attack on this carbon. And you see the product obtained. It is CH3, CH2, CHOH, CH2, CHO like this. Again, it is aldol, no? 1, 2, alpha, beta hydroxy aldehyde. And the final condensed product will be CH3, CH2, CH double bond, CH, CHO. This is A1 attacked on A2. A1 attacked on A2. You can understand it as A1A2 product or A2A1 product. The way you understand it is very important. Isn't that clear? You see, CH3, CH, 1 oxygen and 2 hydrogen out. So CH3, CH, CH, double bond, CH, CHO. CH3, CH2, CH, double bond, CH, CHO. That is A1A2. Either you call it as A1A2 or A2A1, no problem at all. It's all matter of how do you understand. What I said here is A1 forms a carbanion and attack on the carbonyl center of A2. That sense I said. Okay. Now let us think about the reverse. Let us think about the reverse. You have A1 attacked by A2. A1 attacked by A2. This is A1 and this is A2. A2, the alkali attack on this carbon and you get a carbanion here attack on this side. The other way. The carbanion formed on alpha carbon of A2 and that attack on the carbonyl center of the first one. And what is the result? The result will be like this. You get CH3, CHOH, CH, CH3, CHO. This is aldol. Functional group alpha carbon, beta hydroxy aldehyde. And upon heating, you get CH3, CH, double bond C, CH3, CHO, like this. Is that perfect? So, this is A1A2. If this is A1A2, this is A2A1. So, this is what called a cross-aldol condensation. Cross-aldol condensation. There are several this type of condensations. There is Claisen-Schmidt condensation, aromatic aldehydes involving Claisen-Schmidt condensation, Claisen condensation, Perkins reaction, lot of benzoin condensation, right? In fact, you know, you must have the interest to go through various of these kind of condensation, especially you are preparing for IIT exams. If you are preparing for IIT exams, I would say you must go through all these reactions. In fact, in our textbook, we have simple condensation and cross-aldol condensation. In fact, you must go through intramolecular aldol condensation. You must go through intramolecular aldol condensation. I would suggest you to practice. Suppose such a molecule is given to you. Such a molecule is given to you. If such a molecule given to you when treated with a dilute alkali, how many possible products you may get? The maximum number of theoretically possible aldol products, where there involves intermolecular aldol and intramolecular aldol. Within the molecule there can be condensation. Within the molecule there can be condensation. Between the molecules there can be condensation. Within the molecule there can be condensation. Right? I think you have the ability to work out. I think I'll just declare the answer. You may just try how that is possible. You please think yourself. You please think yourself how that is possible. You can get theoretically. When you analyze practically, maybe you are going to get 2 or 3 products the maximum. May not be the greater number of products. But theoretically, when you find such a question, how many maximum number of aldol products are possible? This is kind of analysis you must involve in if you are preparing seriously for any competitive examinations, including IIT exams. Right? Now, in this question, I have given a long chain molecules. Definitely, you will be able to understand intramolecular, there can be cyclization. Let me tell you, you can get 10 possible products. You can derive 10 possible products. Practically, maybe a very few numbers, but still, theoretical answer should be 10. There should be 10 possible products. I'm leaving to you. You just try to find out how it's possible to get 10. And if a small change in structure, the entire answer will change. A small change in structure. This is an unsymmetric molecule. Hope you understand. It's a diketon. It's a diketon which is unsymmetric molecule. Just I am erasing this one part. Just I am removing one carbon. The entire scenario changes. The answer becomes entirely different for the same question. So what I'm trying to tell you is the depth of that particular area which we can go to if you are preparing for a competitive exam like IIT. Okay. So that's all about aldol condensation. We had a detailed coverage regarding aldol condensation and a detailed script or story how the reaction takes place. Okay. Now another very important reaction, Cannizzaro reaction. Next one, Cannizzaro reaction. Cannizzaro reaction, another very popular reaction given by aldehydes without alpha hydrogen. Aldehydes without alpha hydrogen gives very popular disproportionation reaction, Cannizzaro reaction. This is what the reaction is. This is given by aldehydes without alpha hydrogen. Aldehydes without alpha hydrogen give Cannizzaro reaction. Example, if you take formaldehyde, formaldehyde does not contain any alpha hydrogen, even alpha carbon. If you take benzaldehyde, benzaldehyde contain alpha carbon but no alpha hydrogen. They may give, or this type of molecules may give Cannizzaro reaction. Okay. The reaction is the two molecules of HCHO, say formaldehyde, when treated with a concentrated solution of NaOH. Suppose formaldehyde, methanol treated with a concentrated solution of NaOH. You can see this will undergo disproportionation. One molecule will be reduced to alcohol and the other molecule will be oxidized to the salt of carboxylic acid. This is reduction. Methanol upon reduction, you get a methanol, and a methanol upon oxidation, you get a methanoic acid. So formaldehyde upon reduction, you get a methanol. Formaldehyde upon oxidation, you get a formic acid. Since it is alkali solution, you get sodium formate. This is a disproportionation reaction. This is a disproportionation reaction, right? If you take benzaldehyde, which again does not contain alpha hydrogen atom, two molecules when treated with a concentrated alkali, one of the molecule is oxidized. One of the molecule is oxidized and the other molecule is reduced. So one benzaldehyde oxidized to say sodium benzoate and the other molecule reduced to benzyl alcohol. This is what called the Cannizzaro reaction given by aldehydes without alpha hydrogen atom. Once again, the mechanism we don't have to learn in textbook, but definitely you must know the mechanism. Let's see what is the mechanism involved in the reaction. What is the mechanism involved in the reaction? Let's see. This is the story behind. We take molecule number 1. This is formaldehyde, molecule number 1. Of course, I have said two molecules. Now it is interacting with the alkali. Now you see it is polarizing as minus and plus, and this plus is attacked by OH minus. Onto the electrophilic center of carbonyl area, OH minus will attack, and the result will be CO minus HOH. You get it like this, right? Now this molecule will attack the next molecule of formaldehyde over the carbonyl center O minus and C plus, where this bond will break. This bond will break as H minus. Meanwhile, this is electron rich center will compensate for that, and H minus will be attacking over here. It is hydride transfer. That is not a usual story. Usually we find H plus transfer. This is hydride transfer. So H minus transferred to C plus center, and this molecule will turn CHHO minus. And what happened to this side? This side it turned HCOOH, right? Now since it is alkali medium, the acid will be in the ionized form. You get HCOO NO minus, Na plus. If you are taking NaOH, this is product number 1. Sodium sulfoformic acid. This is not that much acidic. This will remain as OH by absorbing proton from the solution. You get CH3OH. Product number 2. That is the story behind. That is Cannizzaro reaction. Disproportionation reaction. Once again, there are variety of Cannizzaro reactions. There is cross Cannizzaro reaction. This is simple Cannizzaro reaction. In the textbook, we are learning simple Cannizzaro reaction, while we have reviewed and notes are written in our classes how cross Cannizzaro reaction takes place, how intramolecular Cannizzaro reaction takes place. Within a molecule, how the Cannizzaro reaction may take place. Between two molecules, how that reaction is possible. And some exceptional cases where even with the alpha hydrogen, where Cannizzaro reaction takes place, like isobutyraldehyde. Hope you remember, it is there in the notes given. That is exceptional, which contain alpha hydrogen atom, but surprisingly it gives Cannizzaro reaction. We have discussed it in the classes, right? And those who are enthusiastic, I would say once again, those who are competitively thinking should definitely go through the reactions like Tishenko reaction, where using metal alkoxide we convert aldehydes with alpha hydrogen undergoing disproportionation. You get alcohol and acid. Further, it is converted to esters. That also we are discussing in the classes, right? So that is about Cannizzaro reaction, very popular reaction given by aldehydes without alpha hydrogen. So two important reactions, aldol condensation and Cannizzaro reaction, right? Aldol condensation given by aldehydes with alpha hydrogen, and Cannizzaro reaction given by aldehydes without alpha hydrogen, right? And coming to an end of aldehydes and ketones, aldehyde and ketone part. This is electrophilic aromatic substitution reaction given by benzaldehyde. Benzaldehyde CHO group is electron withdrawing group. It is deactivating in nature, and of course meta-directing group. CHO group, COOH group, CO group, all are deactivating group. They are meta-directing in nature. So when benzaldehyde, where we have a electron withdrawing group, deactivating group, when taken for nitration, we have NO2 plus as the electrophile attacking at a meta position of the benzene ring. You get meta-nitrobenzaldehyde. Only one product is obtained. Aromatic electrophilic substitution reaction. There we conclude aldehydes and ketones, while our next discussion is on a few topic on carboxylic acids. Already it was dealt in the initial segment starting this chapter. Structural details of carboxylic acid already commented. Structural details of carboxylic acid already commented. Regarding nomenclature, common name, importance of names like formic acid, acetic acid, etc. Some important examples of naming for carboxylic acid: formic acid, acetic acid, propionic acid. This is common name and this is a UPSC name. Butyric acid, isobutyric acid, oxalic acid. Next member malonic acid. Next member succinic acid. Next member glutaric acid. Next one adipic acid. So if you start from oxalic acid, which is a dicarboxylic acid, the next homologue, it is malonic acid. This is oxalic acid, 1 CH2 extra, malonic acid, 2 CH2, succinic acid, glutaric acid, adipic acid. While here we have tricarboxylic acid, propane 1, 2, 3 tricarboxylic acid. All of you know regarding such a system how the naming comes. If you have COOH, CH2, CH, COOH, CH2, COOH, you have learnt this will be the parent chain. If a functional group repeat more than twice in a chain, the parent chain should be taken in that way. This will be the parent chain and it is taken 1, 2, 3, propane tricarboxylic acid, propane tricarboxylic acid, propane 1, 2, 3 tricarboxylic acid, right, which is popular called carboxylic acid or tricarboxylic acid, right. Benzoic acid, phenylacetic acid, phthalic acid. Phthalic acid, there are three varieties. Phthalic acid, isophthalic acid and terephthalic acid. 1, 2 will be called phthalic acid. 1, 3 will be called isophthalic acid and 1, 4 will be called terephthalic acid. And this is the functional group details of carboxylic acid. Functional group details of carboxylic acid. And the resonance involved in there. You can have a resonance here, you get a CO minus, immediately C plus will be compensated, this electron will be shifted to this side. So there is a resonance stabilization over that region. Now methods of preparation, methods of preparation of carboxylic acid from primary alcohol and aldehyde. Already learned, primary alcohols are easily oxidized to aldehydes, from there to carboxylic acid without any change in the number of carbon atom. You see, this is a primary alcohol which is oxidized to aldehyde, from there to carboxylic acid. This is a primary alcohol oxidized to aldehyde, from there to carboxylic acid using John's reagent. CrO3H plus is called John's reagent, right? So that's a simple thing which multiple times we have discussed in the class. While a secondary alcohol cannot be oxidized easily, all of you know. Now from alkyl benzene, that is an important point, alkyl benzene, oxidation of side chain of benzene. Side chain oxidation of benzene can get benzoic acid. Suppose you are taking toluene. You can see this oxidized with a strong oxidizing agent like say KMnO4. It undergo oxidation and the side chain oxidized to benzoic acid. The side chain oxidized to benzoic acid. You get a COOH. And I think all of you may be remembering it happens irrespective of the length of the chain. It happens irrespective of the length of the chain. Suppose there is instead of methyl group, imagine it is ethyl benzene. Imagine it is ethyl benzene. The result is same. If you are dealing with CH2, CH3 undergoing the similar kind of oxidation, the result is same. So if it is 1 carbon, 2 carbon, 3 carbon, whatever it may be, imagine it is 3 carbon, CH2, CH2, CH3. The result is same. Imagine the group is like this, no problem. Imagine the group is like this, CH, CH3, CH3, isopropyl group. The result is same. So whether you have methyl group, ethyl group, propyl group, isopropyl group, no issue at all. No issue at all. And even it can be like this. It can be like this. You see that? CH double bond CH2, vinyl benzene. Vinyl benzene. The result is same. So let it be 1 carbon CH3 group, it can be ethyl group, it can be propyl group, it can be isopropyl group, or it can be ethene like this. This is vinyl benzene, styrene, vinyl benzene. The result is same. But in one case, Please be very careful. You may not get the product. And what is that one case? In one case, imagine you have tertiary butyl group. What is the importance of tertiary butyl group? You have CH3, CH3, CH3. You will not get this. Please be very careful. That in fact may not give you the result. This one case, you may not get that result. And I don't have to tell you what is the reason behind. What is the reason? What is the reason behind? It is self-explanatory. What is the reason behind? You can see in all other cases, the carbon connected to the benzene ring contain at least one hydrogen and it is prompting the oxidation reaction, while in tertiary butyl group, tertiary butyl benzene, that carbon is missing. So that reducing carbon is not present. That's it. That's it. Very simple. Very, very simple. So except that case, on other cases, whether it is 1 carbon or 10 carbon, you get benzoic acid. Irrespective of the length of the chain, you will get benzoic acid. Right? Hope you all you have learned, but I'm just reminding you. So that is the importance of side chain oxidation, which is done by strong oxidizing agents like potassium permanganate or potassium dichromate, like that. At the same time, we are learning in another segment in the same chapter. Few minutes back, we were learning about Etard reaction, where toluene treated with chromyl chloride, we're getting a gem dye product, and hence forming a complex, hence we get aldehyde. That also we have discussed a few minutes back. So that's about an important area. While another one is from nitrile, amides, etc. That also I would like to tell you. Nitriles upon reduction, you can get carboxylic acid. Nitriles upon reduction, you can get carboxylic acid. RCN upon, not reduction, sorry, hydrolysis. RCN upon hydrolysis, either in acid medium or alkaline medium, you can get, it's cleaved over here. It is cleaved over here. You get RCOOH and ammonia. If it is alkaline medium, this will be in the form of salt. If it is acid medium, this will be in the form of salt. It's as simple as that. In either medium, you can conduct hydrolysis. You can think about what will happen in isocyanate. In isocyanate, it in fact is not triggered by alkali medium. It is stable in alkali medium. It is hydrolyzed only in acid medium. Think about why. And what will be the product obtained if you take isocyanate? Okay, I'm leaving to your skill to identify what happens if you deal with isocyanate, carbylamine. Carbylamine hydrolyzed only in acid medium, not in alkaline medium. In alkaline medium, it is stable. Only in acid medium, it will hydrolyze. So the question number 1, why not in alkaline medium? Question number 1. It is hydrolyzed only in acid medium. And question number 2, if it hydrolyzes, what is the product obtained? And why in that product you get a silver mirror test? I'm leaving to you. So acid cyanide or nitrile upon hydrolysis, you will get carboxylic acid. Breaking this region, this C will turn COOH and N will turn ammonia. And according to the medium in which you do the hydrolysis, you get the product. If it is acid medium, this will be in the form of salt NH4+. If it is alkaline medium, this will be in the form of salt RCOO-. Okay. Similarly, almost all acids and derivatives can be converted to carboxylic acid by hydrolysis. As I said, as we have already discussed, RCN upon hydrolysis, you get RCOOH. You can take RCONH2, acid amide. Upon hydrolysis, you get carboxylic acid. You take acid chloride, You take acid chloride. Upon hydrolysis, you get carboxylic acid. You take ester. You take ester RCOOR dash. Upon hydrolysis, you will get carboxylic acid, and this part of the molecule will turn R dash OH, alcohol. And acid anhydride, you get carboxylic acid RCOOCOR. Upon hydrolysis, you get carboxylic acid. So acids and derivatives, when hydrolyzed, you will get carboxylic acid. Nitriles, cyanides, upon hydrolysis, you get carboxylic acid. Clear? Yes. So that is regarding preparation of carboxylic acid. Preparation of carboxylic acid, all these reactions you can incorporate together. This is something different from Grignard reagent. From Grignard reagent, you can produce carboxylic acid from alkyl halides. If you take an alkyl halide, say RBr, treated with carbon monoxide, it is polarizing like this, O minus and plus very feebly. It will break like Br minus and we need a Grignard reagent. We are dealing with a Grignard reagent, not simply alkyl halide. So I am taking an alkyl halide treated with the magnesium in dry ether. You are getting RMgBr. You are getting a Grignard reagent, which will break, all of you know, will break as Mg plus and R minus. This R minus will attack on C plus. And the addition product obtained will be RCOOMgBr. You get such a addition product which hydrolyzes over this region. Subsequently, you get RCOOH, the product we are talking about. So that's how a Grignard reagent, which is produced from an alkyl halide, converted to carboxylic acid. So at the starting point we have only R, and at the end point we have one carbon extra. It is ascending reaction. It is ascending reaction. Starting from a alkyl halide, you can get a carboxylic acid, one carbon extra. Ascending reaction. Is it clear? All these reactions already discussed. Hydrolysis of esters and hydrates, all discussed. That's about preparation of carboxylic acid. That's about preparation of carboxylic acid, right? So from alcohols, aldehydes, side chain oxidation of benzene and hydrolysis of various related products. Now on to physical properties. Carboxylic acid. Up to 9 carbon atoms, colorless liquid at room temperature with the unpleasant odor. The higher acids are wax-like solids and are practically odorless because of low volatility. They are higher boiling than aldehydes, ketones and even alcohols. They are higher boiling than aldehydes and ketones. Okay. But higher than alcohols because of molecular association. Because they got a greater molecular association. Don't you see? Even in the vapor state, especially in organic solvents, it undergo such an association. You see the two carboxylic acid getting associated. RCOOH associating with the RCOOH by hydrogen bonding, forming a dimer. When it makes a dimer, the molar mass increases, size of the overall molecule increases, attraction increases, boiling point increases. It's as simple as that. The hydrogen bonds are not broken completely even in the vapor phase. In fact, most carboxylic acid exists as a dimer in the vapor phase or in aprotic solvents. In protic solvents, they may dissociate. In protic solvents, they may dissociate. So what is happening to acetic acid in benzene and acetic acid in water? If you take acetic acid in benzene, it will associate. It will associate like this, while the same acetic acid in water will undergo dissociation, CS3, COO minus and H plus. So acetic acid in water dissociate, the Van 't Hoff factor will be greater than 1. Acetic acid in benzene associate, Van 't Hoff factor will be less than 1. Abnormal colligative properties we are learning in the chapter 2 solutions, right? Yes. Simple aliphatic carboxylic acid having up to 4 carbon atom miscible with water. See, carboxylic acid up to 4 carbon atom are miscible in water because of it's able to make hydrogen bonding with water. It is able to make hydrogen bonding with water. The solubility decreases with increase in number of carbon atom. Higher acids are practically insoluble because of increased hydrophobic interaction. Benzoic acid, simplest aromatic acid, nearly insoluble in cold water, while they are soluble in organic solvents. Now, one of the very important reaction we are going to discuss in carboxylic acids is their acidic nature. Acidic nature of carboxylic acid, that is the important point. Acidic nature of carboxylic acid. That is an important discussion. We know carboxylic acids, by the name and by the character, they are acidic in nature. How they are acidic in nature? RCOOH. It releases this hydrogen and you get RCOO minus plus H plus. This can stabilize this undergo stabilization. This can give resonance stabilization, giving equivalent structures. You get RCO minus like this. So the two equivalent structure due to resonance stabilization is the reason for reasonably good acidic nature shown by carboxylic acid. So this may ionize like this, liberating H plus, because the anion formed is stabilized by resonance. Right? Now this resonance stabilization is greatly influenced by the stability of carboxyl group is greatly influenced by the R group. If the R group is electron withdrawing in nature, they greatly stabilizes the carboxylate ion. So if you have a carboxylate ion COO minus connected to electron withdrawing group, this will greatly stabilize this system because O minus will decrease. Because it is electron withdrawing in nature, O minus will decrease, stability will increase. When the stability of carboxylate ion increases, the more reaction shifted to right hand side, you get more H plus, it is more acidic in nature. So carboxylic acids are greatly acidic when there is electron withdrawing group present. So presence of electron withdrawing group stabilizes the carboxylate ion and hence increases the acidic nature of carboxylic acid. Hence Ka will increase, pKa will decrease. I repeat, presence of electron withdrawing group will cause greater stability of the carboxylate ion, which will increase the acidic nature of carboxylic acid. Ka will increase, pKa will decrease. You know, greater the Ka value, lower the pKa value, stronger the acid. All of you know that. Greater the Ka value, lower the pKa value and stronger the acid. All of you know that. Okay. So the presence of electron withdrawing group increases the acidic character, while the presence of electron donating group decreases the acidic character. Imagine there is a electron donating group connected to COO minus. It is donating electron density. So O minus will increase, stability will decrease. So presence of electron withdrawing group increases the acidic character. Presence of electron donating group decreases the acidic character. That's a general scenario. Okay. And in fact, a carboxylic acid can be sufficiently acidic. It is interacting with active metal like metallic sodium, liberating hydrogen gas. It is interacting with NaOH, getting salt, neutralization. A very important point is their interaction in sodium bicarbonate. You know, a very simple test for acids is bicarbonate test. It produces brisk effervescence. The production of brisk effervescence using sodium bicarbonate is a very simple and convenient test for carboxylic acid. So all these reactions given by carboxylic acid, and in fact we have seen earlier in one class, comparative these three reactions given by carboxylic acid, while phenol give these two reactions, while alcohol give only one this reaction. We have discussed that. A comparative study of relative acidic strength of alcohol, phenol and ethers. This is the resonance stabilization caused by carboxylate ion. And Ka, pKa values and related points. Hope you remember pKa is negative log of Ka. pKa for hydrochloric acid -7, very low value, strong acidic. pKa for trifluoroacetic acid, the strongest carboxylic acid. The strongest carboxylic acid, trifluoroacetic acid, because this group is highly electron withdrawing group. And the value is 0.23. 0.23. While if you go to benzoic acid, it is 4.19, very high value relatively. And acetic acid again higher, 4.76. So smaller the pKa, already commented, smaller the pKa, stronger the acid. So strong acids have pKa less than 1. While pKa 1 to 5 considered to be moderately strong, while pKa 5 and 15 is weak acid, 5 to 15 is weak acid, while extremely weak means above 50. Alcohols 15.9, 16 alcohols, it is extremely weak. So less than 1 strong acid, 1 to 5 considered moderately strong, and 5 to 15 weak, above 15 weakest. Is that clear? Fine. And this is the kind of explanation which we can give the presence of electron withdrawing group and electron donating group. Please see that. Presence of electron withdrawing group. Electron withdrawing group stabilizes the carboxylate ion and strengthens the acid, while electron donating group destabilizes the carboxylate ion and weakens the acid. Clear? Right. And this order, I would say, you must by heart. This order of various groups, how influencing the acidic nature. You see, CF3 when comes, most acidic. Nitro, cyano, fluorine, chlorine, bromine, iodine, phenyl. It goes like that. And a relative order here. Trifluoroacetic acid, trichloroacetic acid, dichloro, nitro, cyanide, monofluoro, monochloro, monobromo, formic acid. Formic acid compared to acetic acid, you see, better strong acid. Then chlorine goes away. It's very important to see that the strength of acid when you try to predict theoretically. See, practically how we understand strength of acid is based on pKa value. Lower the pKa value, higher the stronger the acid. Theoretically, how you can predict means the same thing when for the questions. You have to see which group is present. You have to see which group is present. You have to see how many of that groups are present. You see, CF3, 3 fluorine, like that. 3 chlorine, 3 fluorine. 3 chlorine, 3 fluorine. Fluorine is more acidic. I mean, when fluorine comes, CF3, CCl3. CF3 turns more acidic. I mean, presence of CF3. So, which group is present? How many are present? Where it is present? See, chlorine is monochloro. Where is monochloro? Monochloro very close and monochloro apart. This is one chlorine on the second carbon. This is one chlorine on the third carbon. Its acidic strength decreases. So, how many chlorine are there? Is it chlorine or fluorine? How many chlorine? Where it is? All this can be utilized for predicting the acidic nature of various acids given. And it should be practiced sufficiently. Okay. Then it is benzoic acid, phenyl acetic acid, acetic acid, propanoic acid, goes like that. So these are important area. Quite frequently questions are coming from. And here we have some substituted benzoic acid, benzoic acid without any substitution 4.19. When there is electron withdrawing group, the value decreases, acidic character increases. While there is electron donating group, value increases, acidic character decreases. You see this? 4.19 without any group. When there is a electron withdrawing group present, this is electron withdrawing group, NO2 group. So when there is electron withdrawing group present, acidic character shoot up, value drops. When there is electron donating group, this is electron donating group, the acidic character decreases, value increases, pKa value increases. Is it clear? Yes. So that is about an important topic from the chapter regarding acidic nature of carboxylic acids. Now a few reaction. First one, anhydride formation. Acids when heated you get anhydride. For example, acetic acid, this is ethanoic acid. When heated with a dehydrating agent like P2O5, phosphorus pentoxide, good dehydrating agent. Water will be eliminated. OH, water is out and you get anhydride, CS3, COO, COCS3, also written as AC2O. This is what called AC. This is what called AC, AC2O, acetic anhydride, ethanoic anhydride, right? Fine. Esterification, already learnt. Esterification, already learnt. A carboxylic acid with alcohol in acid medium, you are getting ester. That is esterification. Esterification, right? And learning esterification, the mechanism is important, even though not meant for the board exams. Competitive exams, it is important to learn the mechanism. How esterification is carried out. How esterification is carried out. Let us try to understand esterification. This is what the reaction. A carboxylic acid RCOOH plus R-OH in acid medium, you get RCOOR- plus H2O. Look at the reaction, the story behind. RCOOH is getting protonated. This oxygen getting protonated. and the result will be RCOH plus OH. When it is protonated, immediately it go like this and you get RCOH plus OH, where you can see the next molecule of, the alcohol molecule interact. Alcohol molecule, oxygen will go for a nucleophilic attack. And the result will be RCOH, OH, OH plus R. You get it like this. Okay. And now this H plus will release, this bond will be shifted to oxygen and this will go as H plus. And in fact, you know that H plus will be captured here. This will be capturing here and you get RCOH, OR dash, OR dash, OH2 plus. This OH group getting protonated. Once it is protonated, it cannot stand there. Immediately it is out as water. Immediately it is out as water, where this one electron will be shifted to this side. And you get RC double bond OH plus. This is out as water, OR dash. And now the last step, deprotonation. This out as proton, deprotonation. You get RC double bond O, OR dash. Ester is obtained. That is the story behind esterification. I repeat, the carbonyl oxygen getting protonated, you get RC double bond OH plus OH. And this polarized giving like this, where the oxygen of alcohol group make a nucleophilic attack and you get it like this. And this H plus captured by OH and is out as, OH2 plus out as water, you get this, and deprotonation, you get ester. That is the reaction. Okay, fine. May not be important for the board exam, but competitive exams, you must practice. Now, reaction with the PCl5, PCl3, SO2, quite similar to alcohol. Quite similar to alcohol. The way alcohol OH group replaced by chlorine. You can see carboxyl group, OH group replaced by chlorine. OH group replaced by chlorine. OH group replaced by chlorine. And all these reactions we are learning in the chapter haloalkane haloarine preparation procedure. The first preparation procedure of haloalkanes from alcohols. PCl3, PCl5, HCl zinc chloride, red phosphorus with halogen. The most important one, thionyl chloride. Thionyl chloride important because the byproducts are gases and they will escape and you will get the pure product. Isn't it? Fine. So the way alcohol OH group is behaving, carboxylic acid OH group will behave. That's it. Simple. Next is reaction with ammonia. Reaction with ammonia. Carboxylic acid reacting with ammonia, you get amide. Carboxylic acid reacting with ammonia, you get amide. RCOOH interacting with ammonia. First of all, there will be neutralization. You get RCOONH4. You get ammonium carboxylate, which upon heating, there will be expulsion of water, H2O, out, and you get RCONH2. This is what the product obtained. You get the amide. And if you try for a stronger dehydration procedure, say with the P2O5, again water will be out and you get cyanide, RCN. Nitrile will be obtained. Right? And already we have seen nitrile upon hydrolysis, you get this. Nitrile upon hydrolysis, you get this. Already we have seen. So try to memorize in that way. Okay. Another important reaction with ammonia, if you take phthalic acid, imagine we are taking phthalic acid. This is phthalic acid. Imagine it is treated with excess of ammonia. Phthalic acid treated with excess of ammonia. The result will be you get ammonium phthalate. You get ammonium phthalate. This is ammonium phthalate as a result of neutralization. And that upon heating, you will get the so-called amide. Phthalamide is obtained. You get phthalamide. H2O will be out. H2O will be out. And you get phthalamide. This is phthalamide. Right? Phthalamide. CONH2. CONH2. You know what happens when this heated strongly? When heated strongly, one ammonia will be expelled. This NH2 and one hydrogen expelled, and you get a cyclic imide. Phthalimide is obtained. Phthalimide. And many of you may be remembering the importance of phthalimide in preparation of certain preparation reactions we are learning in the next chapter or so. This is phthalimide. That is another important reaction pertaining to phthalic acid reacting with ammonia. First you get ammonium phthalate, then you get phthalamide. This is called phthalamide. Phthalamide. Phthalamide on strong heating, you get phthalimide. Phthalimide. Like that. So all those reactions explained here. Then reduction of carboxylic acid. Reduction of carboxylic acid. Carboxylic acid reduced by lithium aluminum hydride, or better reduced by diborane. You get a primary alcohol. Carboxylic acid reduced by lithium aluminum hydride, or better by diborane. You get a primary alcohol. And in fact, diborane does not easily reduce functional groups such as ester, nitro, halo, etc. And even sodium borohydride will not give this reaction. This reaction is given by lithium aluminum hydride, diborane. Diborane will not reduce these groups. Sodium borohydride will not give this reaction. Very important, multiple times came for the exam. And this one, hope you remember, decarboxylation, learning in the first year topic, decarboxylation using soda lime. So carboxylic acid using soda lime, you get alkane. Preparation of alkane, decarboxylation using soda lime, learning in the first year topic, preparation of alkanes. Similarly, Kolb electrolysis, RCOONA or RCOOK. Undergoing electrolysis, you get RR as the product. Kolb electrolysis, RR obtained as a product, along with the elimination of carbon dioxide and hydrogen produced at a cathode, including mechanism we are learning in the first year topic, right? Kolb electrolysis. So all those are related previous learned topic. And one of the very important reaction comes in the end portion of the chapter, HVZ reaction. HVZ reaction, Hell-Volhard-Zelinsky reaction. Those carboxylic acid which contain alpha hydrogen in it, the alpha hydrogen will be replaced by a halogen. Carboxylic acid containing alpha hydrogen treated with halogen and red phosphorus. Halogen means chlorine, bromine. Normally we know that. Usually we know chlorine, bromine. So the alpha hydrogen substituted with one chlorine or bromine, and you get a alpha substituted carboxylic acid. The very famous reaction, HVZ reaction. Why it is very famous? Because at alpha position you've been able to substitute one halogen. So what? So what? So what in the sense? Because it is highly helpful in producing various other useful products. At alpha position, replacing halogen, you can place many other group. You can produce many amino acids, many biomolecules. Synthetic importance is the point. It is able to produce various useful synthetic products. That is the importance of HVZ reaction. That in fact is a very popular reaction dealt in the chapter. Okay. And a final, remember this is the reaction given by carboxylic acid, which contain an alpha hydrogen, and that alpha hydrogen is replaced by a halogen treated with a red phosphorus. Okay, fine. And the last reaction from the entire chapter, which I don't have to tell you, a big chapter in fact. In organic chemistry, this is one of the biggest chapter, I would say, right? The last one is aromatic electrophilic substitution reaction. Aromatic electrophilic substitution reaction. Once again, this group is electron withdrawing group. This group is deactivating group. This group is meta-directing in nature. And you can see when treated for nitration. When you are doing for nitration, you get NO2 plus, which is attacked at a meta position. You get meta-nitrobenzoic acid. Halogenation, you get Br plus, halogen comes at a meta position, meta-bromobenzoic acid. So aromatic electrophilic substitution reaction of benzoic acid, you get a meta product. Clear? Fine. Very important to see that they, however, do not undergo FC reaction. Carboxylic acid, benzoic acid does not give FC reaction. What is the reason? Because the carboxyl group is deactivating, number one, and the catalyst aluminum chloride get bonded to carboxyl group. So that you can have two reasons. One is COH group is deactivating in nature. Number two, the Lewis acid is attacked by carboxyl group. Two reasons commented why they don't give FC reaction. Right? And that comes to an end of the chapter aldehyde, ketone, carboxylic acids. Right? We just started from the structural details, preparation of aldehydes, ketones, various reactions, Rosenmund reduction, Diebol H, Etard reaction, Gatterman-Koch reaction, Gatterman aldehyde synthesis. So variety of reactions, reaction with the dialkyl cadmium, Iodoform Test, etc. Various properties related to aldehydes and ketones, nucleophilic addition reactions, various nucleophilic addition reactions, reaction with ammonia and derivative, heavy acetal formation reactions, right? Then acidic nature of alpha hydrogen atom, aldol condensation, Cannizzaro reaction, characteristics of carboxylic acid, preparation of carboxylic acid, the most important acidic nature of carboxylic acid, and a few reactions including esterification, finally HVZ reaction, etc. A big chapter, a very important chapter from organic chemistry. With another chapter, we will meet in next class. Okay, bye, see you, take care, bye.